All right, so this is going to be your introduction to this. It's kind of like a project. It's going to take a little bit of time for us to work through this next activity dealing with the mathy side of science and climate change. So this one is going to focus on making sense of large sets of kind of messy data. So to get us started, we're going to put our brains back around this idea of Arctic sea ice, which you guys already know a little bit about because of our climate change stuff that we did in Unit 4. You know a little bit more about it because of what I presented to you the very first activity with Unit 5. But we're going to kind of wrap our heads around it one more time. So Arctic sea ice is ice that is in the ocean, either in the Arctic, which is in the northern hemisphere, or the Antarctic, which is in the southern hemisphere. What's interesting about sea ice is that when you go to the ocean, you think, oh, the ocean is salty, so sea ice must be like big salty ice cubes in the ocean, right? Like that's what you would think. But when sea ice forms, it's just the water molecules that are forming ice, right? That salt that's in the ocean is not actually included in sea ice. And so when we talk about ocean circulation and how cold water from the poles returns back towards the equator to be heated up again, it's also being driven by density. So at the poles, because salt isn't being included in sea ice, it becomes more dense, which also causes it to sink down to the bottom of the ocean. Also, because of its temperature, it's being driven back towards the equator. So that's really interesting to think about in terms of what would the long-term effects be on just ocean circulation if we don't have sea ice anymore. And like I mentioned before, there's this normal fluctuation in the amount of sea ice that's covering the Arctic and the Antarctic just based on the time of year, right? Winter time, it makes sense that there should be more Arctic sea ice because the temperatures are plummeting, whereas in the summertime, it makes sense that there wouldn't be as much sea ice just because we're tilted towards the sun, the temperatures are naturally warmer, we're getting a more intense solar radiation, so we're not going to have as much sea ice. So I found this YouTube video. I thought this was interesting to see and look at. I'll turn down the volume a little bit, kind of talk over it. So the title of this is Large Iceberg Breaking Near Ilulissat. I don't exactly know how to say it, but I Googled it, and this is on the north, south, east. It would be the west coast of Greenland. Okay, now, believe it or not, there's this super tiny little community over there, and Arctic sea ice will come and reach them. Okay, so when we talk about the growing and the retreating of the sea ice, this community will see it pretty firsthand. Now, this video is showing huge icebergs. Okay, now you're probably looking at this and being like, how big is that? Well, look how big that is. There's birds above it that give you some perspective of how huge this actually is. So I'm gonna fast forward just a little bit. We're not gonna watch the whole thing because this person, whoever is filming, ends up going on a hike and yeah. So when we talk about melting sea ice, it's not just how ice sits in your glass and then it just melts and you don't notice it and you're like, oh, look, I have no more ice in my glass. It's not a peaceful procedure. At some points, it can be relatively violent. And effects of this could be miniature tsunamis, right? You see this person taking a hike because he's like, you know what? There might be some waves that come along and could easily sweep me up right off of the side of that hill there. So in case you haven't in case you haven't watched Planet Earth, right? This is what we're talking about. Okay, we'll pause there. Let's come back and talk a little bit more about sea ice. Other things, I know this was brought up in one of the chemistry hours. How do scientists know what is happening to the sea ice, right? They clearly have data and stuff, but where do those data points come from? And it's all from satellite imagery. So they started collecting data in 1979. They've been collecting it monthly ever since. So we're going to hop over to this YouTube video and just take a look at how NASA is using it to interpret, what's happening. Oh, you know what? Oh, there it goes. Perfect.
In 1978, satellites began continuously observing the polar regions, and the dynamic beauty of the Arctic sea ice was revealed.
Notice that this
What
is
we
starting in
expect to be a solid mass of ice is
2017.
actually in constant motion. As researchers continue to seek a deeper understanding of this region, new information about how sea ice changes is coming to light.
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at...
So that video that we just watched, this one, remember I told you that they experienced sea ice? So it was on the West Coast, somewhere along in this little bay area around in here. That's that previous video. To get perspective, in case you were really into the whole Alaska thing, this is where I was living, right? This is our geographic North Pole. And then I'm going to rewind it a little bit. They're going to talk a little bit about the ages of ice, which is a dynamic that we didn't talk about in class previously, but it's pretty interesting.
In this animation, we're taking Arctic sea ice into the third dimension. Here, we're looking at the ice age, which is an indicator of thickness. Generally, older ice is thicker ice.
That's the voice of Dr. Walt Meyer, senior research scientist at the National Snow and Ice Data Center.
So we're in 1987
What you see in this animation is the ice pulsing out and in with the seasons. In winter, the ice grows out and expands outward. In summer, it contracts inward as it melts. You see the whiter ice, which is the older ice, moving around the Arctic, being pushed around by winds and currents that move the ice. Over the years, the ice pulses around and moves around towards the top along the coast of Greenland. The older ice eventually moves out of the Arctic and into the North Atlantic, where it melts. The ice gets replenished within the Arctic because some of the ice survives each summer and grows older. And particularly in a region north of Alaska called the Beaufort Sea, where the ice spins around in a clockwise direction called the Beaufort Gyre. And that ice can keep spinning around oftentimes for several years and gradually getting older and thus getting thicker. Eventually, the ice will spin out of that gyre and go out through Fram Strait. In the past, we've always had enough ice growth and ice aging, enough ice surviving the summers to replenish the older ice that's lost. But in recent years, we've seen less replenishment. There's been more melt during the summer, so the ice that goes out through Fram Strait has not been compensated by the ice growth. In addition, especially in recent years, we've seen some pretty remarkable things in the Beaufort Sea, where that area that used to be a nursery for the development of the older ice allowed the young ice to age and mature. What we've seen instead is the ice is now more broken up, more scattered, and that's allowing the older ice to melt within the Beaufort Sea. So we're seeing the Beaufort Sea go from a nursery to a graveyard for older ice. As we get towards the more recent years, much of that oldest ice, the ice that's older than 5 years old in the bright white, has almost virtually disappeared from the Arctic Ocean.
Which is
and
crazy
the Arctic
to
is
think
now
about.
dominated by younger and thinner ice.
So this Beaufort, what do they call it? Gyre, right? That's where we kind of retain a lot of that older ice, and it keeps moving, and we can bring in new ice that like just formed and kind of mix it in with it and let it age a little bit. And that's how we can keep this polar ice cap living, right? But if we don't have any new ice that survives, then we're just relying on old ice, but the old ice keeps melting. And so then this is the scenario that we're in when we look at comparing like 1984, where we have a lot of really old ice compared to 2016, where there's not a whole lot left, right? I thought that was a really like interesting phrase, saying it goes from a nursery to a graveyard. Scary. Okay. Coming back, so there's a couple other things that you need to know about Arctic sea ice and the importance of it. This is just coming back from, or referring back to what we learned in the climate change part of Unit 4, where we looked at like absorption and reflection in Earth's energy budget, right? When you look at pictures of sea ice, you notice that it's this really beautiful white, bluish color. And you can imagine, covering an expanse this big, how much solar radiation is going to be reflected off of it, right? And that's a good thing for us because that means we're kind of keeping global temperatures down, right? Where if we're not absorbing it, we're reflecting it, then we're going to keep ourselves cool. But if we don't have that polar ice cap there, then we're revealing this huge expanse of dark ocean, which means now we're absorbing a lot more solar radiation, and that's going to cause our global temperatures to increase. So we're going to take a look at one more video. This one is coming from a group called OceanWise that just explains what is the importance of Arctic sea ice.
When it warms, Arctic sea ice is melting. But why should we care? That's where Eric Solomon comes in. He's the director of Arctic programs at OceanWise.
There are three key ways that sea ice has a global impact that affects all of us.
Air conditioning. The sea ice has a white surface which reflects the sun's energy back into the atmosphere, helping to keep the planet cool.
The less sea ice we have, the more open ocean we have. And the more open ocean we have, the more the sun's energy is absorbed by the ocean in the form of heat.
Jet stream. The jet stream is a fast-moving air current that circles the northern hemisphere, separating cold polar air from the warmer air in the south. As the Arctic warms, this temperature difference decreases. There's increasing evidence that this is weakening the jet stream.
That means it lets warm air high into the north and it lets cold air down way into the south. What we end up with is things like snowstorms in the southern United States and record-breaking warm temperatures in the Canadian Arctic.
Ocean currents, and one current in particular called the Atlantic Meridional Overturning Circulation.
We call it AMOC because who wants to say that other thing more than once?
AMOC is a major Atlantic current whereby cold Arctic seawater sinks and flows south along the bottom, being replaced by warm tropical water flowing north along the surface, forming a cycle.
That warm water is what actually keeps Europe warm for most of the year.
Scientists think that this current could be disrupted by melting sea ice, which dumps a load of fresh water into the Arctic, reducing saltiness and water density, potentially slowing the current.
That increase in fresh water could actually slow or even stop this AMOC system. And that could make Europe a very uncomfortable place.
So things look pretty dismal. Is the future really all doom and gloom, or do we still have hope?
I have a 16-year-old son, so I have hope for the future. I have to have hope for the future. And I think I have a lot of confidence in people's ability to not just adapt, but to really make the kinds of changes that we need to make to see a real difference.
Cool. So if you want to rewind that video and recap those 3 ways that Arctic sea ice can impact our lives, you can just rewind to this one. Otherwise, you can YouTube it. It's Why Does Sea Ice Matter by OceanWise. All right. So there's kind of our recap, our overview of this problem that we're trying to digest about Arctic sea ice and its melting, right? Now, previously, you guys had graphed the average monthly Arctic sea ice extent, but you had done it for the month of September, right? This is a graph that shows the average monthly Arctic sea ice extent during the month of October. You're probably going to look at it and say, wow, that looks like really similar to the graph that I did, and that's probably about right. And then notice that they did a trend line. Notice it's a straight trend line, so they did some real mathy math to get that. Again, probably similar to the trend line that you came up with on your own worksheet. So how do we make sense of data that takes place over such a large spatial and temporal scale, meaning it covers a large chunk of land in addition to covering a large time scale, right? Temporal meaning time. So over many, many years from 1979 till current, how do we make sense of all of that data? There's going to be 4 things that we take into consideration. The first one is when we look at large scale data, we want to look at what's actually being represented in that data. So what are the variables that are being measured? What was the time period that the data was collected in? What are just the basics of that data set? The second thing is generalizability, which I have to say that's super slow, otherwise I miss syllables. Generalizability. So we want to know if the data that's being presented is is representative of only a small chunk of land, like smaller area, or can we use that data set to represent something on a more global scale? This comes back to when I introduced our Lake Superior trendline stuff, and we were looking at the winter of Michigan being not necessarily representative of the entire rest of the world, because that map showed the entire rest of the world having like warmer than average winters, but Michigan was like a small little thing that was just an outlier, right? So generalizability, can we use this just for locally, or can we globalize it? Then the last two deal with short-term versus long-term. So remember, short-term is more on a year-to-year basis. Can we, take what's happening and be able to predict what the next year is going to be like, versus the long-term, where we look more at the trend line to determine, in the next 10, 15, 20, 100 years, can we predict what's going to be happening? So I'm going to do an example here that talks about Arctic sea ice. I'm going to go through all of the answers for this very first row on the Google Doc that's in this assignment also, that's called 2.1 Finding Patterns Tool. You are going to be responsible for filling out this very first row as you watch this video, or you can wait and then click through the slides and copy and paste there, whatever floats your boat. I'm not going to do this last column because that's going to happen later in this week. So let's take those 4 considerations and look at Arctic sea ice. So the first one, remember, was all about representation. So what are the skeletons? What are the basics of this data that we're looking at? So the variables that are being presented, we're looking at the extent of Arctic sea ice measured in million square kilometers. So notice that in my answer, I included what was the variable being measured and what was the units that it was being measured in. For question number 2, it says what time period is represented. I wanted to include the fact that there are data points for every single year within the time range of 1978 to 2013. It wasn't every 5 years within that time interval. It wasn't every 10 years. It was every single year from 1978 to 2013. Another important factor with this data is that this data was collected during the month of October, not during any other month, simply October. The next couple of questions deal with generalizability, meaning the data points that were collected were from what region across the globe. So remember, I told you that sea ice can occur either in the Arctic or in the Antarctic. Now, this graph is specifically showing the patterns in Arctic sea ice extent, which means this is only happening in the northern hemisphere. Okay, so the regions that's included, more so in the geographic North Pole, this is not representative of the South Pole. Oh yes, and that leads in question number 4. What does this tell you about global patterns? Again, it only reflects what's happening in the northern hemisphere, not in the southern hemisphere near the Antarctic. Questions number 5 and 6, dealing with short-term variability. Question number 5, describe the short-term variability in the data, meaning what happens year to year. Well, looking at the graph, right, we can see that at some points the amount of sea ice decreases, at other points it greatly increases, and then it'll decrease again, and then it'll increase again. And I want you to imagine that you're following along this line, right, and you're asked to plot the next point for 2014, 2015, 2016. Only using the data points that are already given, could you do that very easily? Not necessarily. It's pretty inconsistent. In fact, the amount that the sea ice grows or retreats is inconsistent also. So we would say that this data is pretty unpredictable on the short term, right? If we were to say what's going to happen with the amount of sea ice next year, we're not entirely sure, right? However, if we look at the long term, so in questions 7 and 8, according to the trend line, it's very clear that Arctic sea ice follows a negative trend, which means as time is going on, the amount of Arctic sea ice coverage is decreasing. We could possibly predict that in the next 2, 10, 20, 30, 50 years, that there's still going to be less and less Arctic sea ice. Can we predict a specific amount? Maybe not necessarily, right? That's kind of going back to the short-term thing, but we know in the long term, there's going to be less and less Arctic sea ice. Okay, hopefully it's not too difficult. You can go back and review my answers for all of those using the slides or this video to get this first row of your Google Doc filled out. In the afternoon time, we're going to break off into smaller groups, and each of you are going to be assigned in a group to study one of the following phenomena, either global temperature, sea level, atmospheric carbon dioxide concentration, or atmospheric carbon dioxide annual cycle. And you're going to be looking at graphs that are of the large scale, a little bit messy data, and you're going to have to use these 4 considerations to make sense of it. I will say that this is going to be kind of time consuming though, because there's other tasks that you're going to have to do to become more knowledgeable of the situation and what it means and what is happening to it. But we'll get more into those details in the afternoon time. Your job for right now is just watch this video and then fill out that first row in your Google Doc. Alrighty, that is all I have for you. Hope you found it interesting, and we'll see you in the afternoon.